Okay, so as of like the the last few days, like let's go to my notes. Like I feel like I've covered all the math stuff. So like as I said on the first live stream, time to get started. But as usual, not so fast. Let's take a bit of a detour. Or rather we have kind of like the math behind just generally like neural networks, like very basic, like just enough math that I feel comfortable like using a library like TensorFlow to just handle the neural network for me. Now like there's like this video again, this playlist right here that like is pretty much like perfect, I feel. Like really perfect. Just copy that and open it here. And like especially important is like this lecture number 3. Like that's very important. And I think after doing that, like watch that and then like I should like just pause, like kind of think about the chain rule myself, like have some like kind of like try to like imagine exactly how to implement this back propagation, and then in chapter 4 like confirm it. And also like this links like all these lectures, they link to like this book, right? There's like a book. Uh there was this like book, maybe this one. Right. So like this one right here, right? There's like a right. I believe I actually read this a few years ago. Like there are like several chapters. I read like the first one. Yes, and now it's stochastic gradient descent. Well, I believe I kind of stopped around like here, and I kind of like just skimmed this a bit. And yeah, this chapter 1.html. And I basically like stopped at chapter 2 and I kind of looked at that bit and then I just stopped because I felt like chapter 1 kind of along with these these 4 videos like kind of satisfied my intellectual curiosity, like yeah. Okay, so yeah, so like the next step of course is like, well, also like the next step like to kind of shore up gaps in my knowledge or anyone else's that are watching this, like just I went over all the math stuff that I felt was pertinent. And then like there's the playlist and then there's like this course here which I admittedly I kind of forgot a lot of the stuff, but like I mean ultimately just like everything is like just Bellman this, Bellman that, like just states, actions, like the state action pairs, like the Q value, and then like given a state, you want to know what action to take to get like the best expected reward at the end after all the state actions, like the whole trajectory of like choosing your actions until you hit some like reward at the end. Like yeah, good stuff. And then this is like the like finally like this is like the last little thing to cover right here, like this link that I have opened up. And like just before like starting streaming this, I was like kind of looking at this, reading this, like kind of refreshing this in my mind. And because of this, I've kind of realized that like I've also like of course read the I've read like the AlphaGo papers for like AlphaGo Zero, like not just for Go but also for their papers on chess. Yeah, like yeah, these were like in the same paper. Like there are actually several papers, but um like the thing is like I'm basically like using the stream to like kind of talk about like I'm going to take a detour to like Connect 4 because well it's also I used to love that game a lot. It's like one of my like before I got into chess, I mean that was like kind of I believe that Connect 4 was solved, I think. So like yeah, it's a solved game, but it's a nice toy example. So like one of the things like I'll just like skim over this again. But like one of the things is like this actual neural network that you use for like AlphaZero, like is like to actually design this neural network, like in terms of like my game BumperCoins, the issue is like it's a very at least to me, I don't know like what these days it would constitutes like a large model because like models are huge. Like like I'm coming from like 2014 knowledge, like when I took my first introduction to AI class in 2014. In 2015 summer, in the summer of 2014 I took it. I got an A obviously, but like yeah, but I was actually like I worked for I was like part of the core staff on 2015 as a reader. Like I kind of like but anyways, the point is that my knowledge for like neural networks is really outdated. Like it's from like 2014. Like the nice thing about like the math stuff I went over is like that's just kind of math. It's kind of like set in stone almost. Like it won't change. But like I mean like right now like networks like my basic knowledge is just like simple perceptrons, like multi-layer, like just MLPs. And then like I guess like for this game for BumperCoins and maybe for Connect 4 too, like I'm going to like use a convolutional neural network, just a CNN, but I'm not gonna like use like a R like a residual neural network, RNN, like ResNet or whatever. Like just I'm just going to like use very simple stuff basically. But like the reason I'm going taking a detour for Connect 4 is that like yes, this like representation of BumperCoins is like very big for the inputs and like also the policy vector is also going to be like extremely big too. Well, first of all, my game is a real-time game, but like because of the energy system, it kind of becomes like it's kind of like a hybrid between a turn-based and a real-time game. That's why I'm kind of applying AlphaGo 0 like to this because like it's actually for turn-based games, not RTF. But like given one coin in BumperCoins, like you can like there's an infinite amount of actions you can do. And also like the locations of it, like it's not like a nice grid. Like there is a grid in BumperCoin, sure. Like let's just take some random replay. Let's see, I play as dev. Let me just take this random game right here. Or actually I want to see what some guest played. Let's see what this guest played against this other guy. I see he's been playing a lot. Right. So you can launch coins. Oh, also in my bots, I'm going to ignore the wins. The wins are too complicated. Let's just forget about them. Keep it simple. Now you see these grid lines, right? There's like a 15 squares down, 20 squares wide, a 15 by 20 matrix. Now, these grid lines, I mean, they're used to like align the obstacles, but like they're just like they're not actually in the game state. Like they're just like for visual, just for the aesthetics. But like the point is that like this is a continuous game, like continuous space. So the action space is continuous. You can launch it like, you know, full pi over to like full 360. Like, I mean, like you have infinite number of vectors that you can take actions from in terms of the direction. And the length, yes, you're constrained by energy levels. Oh, the game's almost over. Yellow, this guest is really bullying Lee. I feel I watched this replay several times. Yeah, there's something really elegant, like, I mean, not elegant, just very, like, cute about, like, using the king to kill the king. Yep, game over. But, like, anyway, so I'm saying the actions are at like, a continuous action space, so, like, I'll have to discretize them. I was thinking of, like, doing either 8 or, I think, like, instead of 8 cardinal directions, I could just do 6. And then, like, here's the kind of the actions. I'll have, like, 1, 2, 3, 4, 5, 6 directions, and 2 intensities. So like 6 at like some percent, like a strong launch, and a half of that. So there'll be like 12 like kind of actions, like flicks of coins, and 1 pass. Just like in Go, like there's like 1 pass too. So like in terms of image planes for I mean, in terms of like the policy vector, like for like basically a neural network will be very complicated or like very well, not very, but it'll be kind of be like the actual like what's that called? Miro, the whiteboard. Like representing this thing, like first of all, like you have to discretize the action space and then like the state space too, because like these are kind of like the coordinates of each coin is actually continuous. Like there's no like they're not like aligned. So what I'm gonna do is like, I'm just gonna like discretize this game, like abstract it into a 15 by 20 game. So like in here, like this is the center. It'll probably be like best fit in this square. So like when you kind of take this game state and discretize it, like this will be kind of in this cell right here. This one would be in this cell, and so forth. Like everything will be kind of discretized. So like we're gonna kind of discretize the state space and then like the action space. Like the actual image plane like would look like there'll be like several image planes. So like given like this state, like the neural network for like this game, BumperCoins, would be like kind of there'd be like several image stacks, right? Like kind of there'd be like an image stack of like, you know, like 15 by 20. Like this would be like kind of 15 by 20. And there'd be like several of these planes, like in an image stack, right? You'd have like one just for like the current, like there'll be like the top two planes would give you all the coins for like the current player. Like this would be a 1, and everywhere else would just be like 0 everywhere else except like this one lone 1 for where the king is, like this coin. Then there'd be like ones, or not ones, in fact there should be like health. Like this would be like, let's say like the king has like 75% health, right? Then like if like the king has like 75% percent health and the king is located near the center, like you'd have like 0.7, like 0.75 as like one of the entries in this cell, and everything else would be 0, right? And then like let's say like we have some coins like the same, like this is like the current player. You'd have like one coin here with like 1 health, one coin here maybe with like 0.5, 0.5, and like and so forth. And then you'd have like, so these both planes would be like for the player to move, like the player to move, or like the current player, like the player whose turn it is, player whose turn it is. Like the neural network doesn't really care about like player 1, player 2. It cares about like, hey, like given these images, like given like this kind of image, like these cells that represent the game state, like whose turn is it to move? And like from that, I'll give like the neural network will like kind of give an evaluation from the perspective of like the player whose turn it is. It'll give a score between like -1 to 1, and it'll give a distribution of all the actions that it kind of thinks this player should take, the probabilities. And you'd have like kind of 2 more planes that like do the same exact thing, but for the other player, other player, and then the actions, right? And then like the outputs of this vector are like just a single, like the value of like this state from the perspective like given by the, like, you know, like I already explained that, just like a single number. But then like so far like the input looks pretty complicated. It has like four input planes, right? Each plane is 15 by 20. So you have like 15 times 20 times the number of planes. And like of course like here like we'd have like another plane for like, let's say the obstacles, right? We'd have like another plane for like obstacles. Like it would have like 1, 1, 1, 1, and like kind of like 1, 1, 1, 1 to like denote that, like putting ones in the locations of all the obstacle cells. You have like 6 ones here and like 6 ones here. And like actually this plane is just pretty much like constant maybe, but like this is obstacle plane. It's the binary plane. And as for the energy system and like the player's energies, for now I'm just gonna like reduce it to a purely turn-based game, right? Like for example, like the yellow would make one turn, then the blue would make, then the silver would make one turn. So golden moves 1, silver moves 1, golden, silver, until the game ends. So I'll basically kind of like make it a purely kind of turn-based game. So I won't have to worry about like, because like if I want to be like super fancy, I could add more image planes where like there's this technique I noticed like where you have like a a constant value plane where like if one thing has energy of like 0.9, like I mean like yes, you have to like kind of like I believe in like kind of in neural networks it's kind of good to like normalize everything, so everything is like between like 0 and 1 or maybe -1 and 1, I don't know, but the point is that like everything is normalized. So instead of like I believe like in an actual like game like there's like some high number like 300 something energy units, but everything is like normalized to that. So like if you have like the point is that like if you have like let's say like right here like there's like let's say like about 20% energy, then like you could have like every single cell in this thing be like 0.2 0.2 0.2 0.2 and like so forth dot 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 dot, like the whole thing would be constant value. But I'm just gonna ignore that, like, and keep it very simple and just have it be like a nice turn-based game. So we're gonna have like 5 planes I think so far. So like you'd have like 15 times 20 times the num planes, which would be 5, so that's like already a pretty huge number. And that's just the input, so the input is pretty complicated. Now like I'm sure there are other ways of like architecting your like inputs for the neural network, but like this is kind of like similar to like the architecture that like chess uses for instance, to a like a set of image planes. So like and like Go too, like set of image planes. And like convolutional networks, like you apply like a convolutional layer to this convolutional filter, and like anyways the point is that like and like yeah, if you look at like image recognition, right, like in terms of like image classification, oftentimes we have like 3 channels, like we have like 3 image planes here, and like this is like the canonical like very similar, like you have like typically like an RGB, like this would be like all the pixels that are like red, like let's just say all these pixels are red, and then like between 0 and 1 representing like how turned on it is, or maybe it's binary 1 and 0, I don't know. You have R, you have G, and you have B. So basically like an image could be kind of like into these channels. Well, each channel, like you have an image stack / channel, right? So like in this case, like we have like it's like kind of like the same principle where like the R channel, green channel, and B blue channel, like RGB, are kind of like a logical unit. Like everything is like in terms of like split by channels. Kind of similarly, like conceptually, like that's kind of like the same concept right here, where like you have like different planes for like kind of each, like they're kind of distinct, like, and like every plane is 15 by 20, so like everything kind of lines up to the overall geometry of like this image. Like in theory, like we could actually like train a network on the exact pixels. I think like Q-learning, like one of like the deep Q-learning, like Q-start, like there's like some famous like Atari paper where like they do reinforcement learning, and like the computer like does not know the rules of Atari, it just kind of sees the pixels, and from that it like learns how to play. So like we could have been past the pixels, but like since I have full control of the game state, like I don't need to like, it's not like it's like someone else's game and I'm like building a bot for it where all I can do is sample their pictures. I have full control of the game state representation. So like that's kind of how I plan to eventually represent it. But the point is, this is super complicated, so training this network might be a huge hassle, so I'm going to start off with a simple example of Connect 4. But anyways, I mean, actually, I mean, this is our like kind of our game state. Like this is our like kind of input layers, our input shape of like our input shape, right? This is kind of how the inputs look, and the outputs are going to be like, again, super complicated too. Like our policy which we return will be like a giant, a very, very, very large, like thousands, like very large, I want to simplify it, but like a huge, yeah, of all possible actions. So like, again, like there'll be like how do we actually represent this? Again, like I looked at the AlphaZero paper for chess, and like basically like there'd be again several planes. Like let's pretend that like we have like just 6 directions, right? I could do 8, but I just kind of feel like keeping the number as small as possible. 6 seems like a good number because like you have like one from both sides, like covers the horizontal axis, and then I mean if you look at like this, just to me visually it kind of looks a lot like, oops, the the actual like game itself. Like 6 feels like a nice number to me. I don't know, it just does. Let's say that we can like kind of like do this, and like kind of like we have like 12 options, right? Like, or let's just say we have 6. Like, forget the 12. Like, we can only like shoot 6 in a pass, right? So like for each of these 6, it's again kind of like we have like 6 planes, so to speak, right? We're like 1, 2, 3, 4, 5, 6. We're like, this is like direction like 1, that's direction, or let's just make it direction 0. And that's direction 1, that's direction 2, that's direction 3, that's direction 4, and that is direction 5, right? So this plane corresponds to direction 0, dot, 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 and like this plane corresponds to direction 5. So now, like, again, this is a grid, right? So let's say that we have like point 2, and like here like point 7, right? And maybe like here 0.1, and everything else is 0. I think like the idea is like you'll apply softmax, right, at the very end, like some like basically like when the network like learns a lot, like it'll kind of realize that everything has to sum to 1. I think like there's an activation function called softmax or something that like might like kind of enforce that everything sums up to 1. So here what it means is like if you have a point 0.2, 0.7, 0.1, that means like everything else is 0, which is, that means like if we have a coin and like this kind of, let's say this is like 2 and 2, like this is 2 and 2, then like this coin at like 0, 1, 2, 0, 1, 2, like there'd be a coin right here, and that coin with 20% confidence, we want to launch it in the direction of 0. So like that means like this kind of like thing means that like we would like take this, and like with 20% we want to launch it here. So like again, like everything is very like, everything is like in terms of image planes, it's very visual. So like there's like a nice one-to-one correspondence with each cell and like how it actually represents in BumperCoins in my discretized model of it, right? Very, very neat. Now like, yes, we could actually like have this as output, but again, like we'd have to actually like double these and add like 6 more planes for like the double, because like we want to have like, it's not just like, I want to kind of give a mix of like hard launch and a soft launch. Like one option's like, hey, like why would you ever want to like do a soft launch when you can do hard launch? Well, like let's say you have a coin here and a coin there, and let's say like if this like does a hard launch, it lands here, right? Then it'll get punished. So maybe instead it wants to kind of like gradually kind of like, instead of like going there, it'll be really punished next turn. So maybe it wants to like lower the gap by a bit, and then like this guy, if he has a hard launch, he may hit this, but the end result after contact would kind of like, they'd collide, like this one would go here a bit and this one would go here, and this thing can like do a kind of a comeback. So like the point is that like it may make sense. It might be like it'll add, I feel, more richness to the gameplay, where you can kind of like, also there'll be a pass action too, pass, just like in Go, like pass. So like we take this entire plane, right? We take this like stack of like kind of these numbers, right? Like this is just like one big tensor, and like we kind of flatten it, and then we add an extra cell for pass, right? So at the end, like all these like cells like kind of get converted to one huge list, where like, say the last entry is like the pass, and then we have like, let's just pretend that we only have one direction for now, just for simplicity, and like we have like, so that's like 6. So you have like 5 lines, like 1, 2, like 1, 2, 3, 4, 5. So that's 1, 2, 3, 4, 5, 6. Where each of these, like this kind of corresponds to 0. This corresponds to 1, dot, 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 dot. And this corresponds to 5. So in this example, where like we only have like just one, like we're only launching on like one intensity, like this would be kind of like, we'd have like a 0.2 somewhere here, and then like a 0.7 kind of pretty close to the end, and then this is kind of like, and then you'd have like a 0.1 like, again, fairly close to the end, where like how do we take, so like this is kind of like taking everything and flattening it. Now like you may ask like, how do we know, like, in a given stack, like, how does one plane here, like, how does this transform to, like, a single segment in our list, right? Well, I mean, it's like a pretty common pattern where, like, you kind of go here, then you go here, then you go here, and so forth, right? So, like, if you have, like, a row index and a column index, right? Then, like, the, let's let C be, like, this, like 20 in this case, and let's R be like 15 in this case, where R is the number of rows and C is the number of columns. And you have like IJ, right? Like the I, like the, this is like the row index, like row index, and this is like the column index. So like, I guess R and C look a lot, I'll kind of do that, like kind of show that's R and that's like a C of J, right? So like given like I and J, like how do we actually like flatten it out? Like what is like the connection? Again, like if you have this cell at row I, then like what is like the index? Like what is this index, right? Like this maps to like some index and like when you flatten it, right? So like this index given like IJ, right? Given IJ would simply be so like it's in the ith row. Everything is zero index. Like the fact that we're having things be zero index is precisely what allows us to do this. We take I and we multiply it by R. Wait, no, sorry. We multiply it by C, right? And then we add J to it. This is how we like, this is the index here. Like for example, let's just say that like we're working with like just a 4x3 thing, right? Like 0, 1, 2, 3, 0, 1, 2, right? Just a nice 4x3 n by n. And we want to know like where this box right here ends up, right? At like 1, 1. Well, we know it's like kind of 0, 1, 2. Like if we do like this kind of this approach, then this approach, then this approach, then this approach, right? 3, 4. Like we can double check this, right? So if we plug this into the formula, where like we plug in like 1 here, 1 there, and then what is C, right? C is like the number of columns, right? So that's 1, 2, 3. C. Then we get 3 times 1, I, plus 1. And this would give us 4, which indeed is like the index here. In fact, like kind of, this is like kind of how we like took this and like that. And like the same principle here, like just how we add segments, right? Like 0 to 5. Like this like basically like to compute like the overall index, right? We do something similar, like precisely what we did here. Like now, like the index for like, let's say this 5, right? Is now like the index, just like we had index of ij. Now it's kind of like we have like, let's say C ij, where C is the channel, right? The channel size. So like we have like 0 to 5, right? Or it's a channel index. So actually, yeah. So C is like the channel, as in like the direction. Actually, yeah, let me call this D. D is the direction. I and J are like in the image plane, like which ones you have, right? So like to compute this, like what position it is on this vector, right? In this flattened vector, what we do is we take the channel size, which is like the num rows, 15 in BumperCoins, num rows times the number of the number of columns. And this like number of rows times number of columns, like this basically gives us the size of each channel, right? And this is conceptually exactly what we did right here. Like this C, right? the number of columns is the size of the rows. We're just generalizing that. Like this is like kind of like the size of like D, the direction, right? So this is the size. We take that and we multiply that by D. So let's just say that we're working on the zeroth, right? Let's just say that like we're working on the 0, right? That means we're working on like this zeroth plane. Then this term gets zeros out. So whatever like kind of stuff we get here ends up like kind of exactly like, yeah, like everything ends up like in the first segment, like the offset is zeros. And this whole thing relies on zero-based indexing, right? So then we just kind of copy the exact same thing we did here. So this specifies our direction. So after we do this multiplication, we know like the offset, like this computes like if you're in like the first plane, right? Then that's 1. That means like this whole thing works out to be like if D equals 1, we just get like whatever the number of rows times the number of columns is, right? So like if D equals 1, right? Then like this expression right here, it basically kind of covers all these indices and maps us at the top left corner of this first plane, right? That's pretty neat. That's kind of property zero-based indexing. Let me just copy this right here. We take this I times C plus I times C plus J, where C is kind of like the number of columns, which is kind of the size. Actually, instead of IJ, I'm going to make it R and, oh, sorry. Let me just try, is there like a way for me to, yeah, it's kind of select. Wait, no. What I want to do is I want to like do some selection. Select. Just delete that. Just delete this. You delete this. Delete that. Delete this. Delete this. Wait, no, I do not want to delete that. Sorry, I want to delete this. Delete this. And delete this. So like this would be D, right? Like this direction, like which direction we're doing from 0 to 5. And then this would be instead of I, right? Like I is kind of like the R, like the row index. Let's just actually call that R. And this is a C, the column, right? DRC. Oh wait, there's a conflict. Okay, this will be a capital C. Or yeah, this will be a capital C. But anyways, the point is that like, and that is the number of columns, which is, and the number of columns is in fact kind of like, I'm kind of like emphasizing kind of the connection between, let's call this like this whole thing is like the size of all the durs, the directions, right? Like when I say size of direction, right, durs, it's like the size of the image plane, right? So like each direction has like this much size. And like in terms of RC, like each row, like what's the size of a row, right? Like, hey, like given like this particular row here, what's the size of it? Well, that's just its length, which is the number of columns. Like the size of mirrors being updated, reconnecting, to stop doing that, of a row. And then that's like, more specifically, it's number of cells in image plane, image plane, in plane, corresponding in plane of direction. Each direction has its own plane, associated plane, which we kind of stack them all together. And this is the size of the row, which is the number of cells number of cells in a row. So it's like a coordinate system, like DRC, like in terms of like all of these, like D specifies like the coordinates for like the planes. Like the plane coordinate specifies like which plane you're in. And then like once you kind of like see that coordinate, then it's in terms of like row. So like now for a particular plane, like the D specified which plane you are, and now the plane has a bunch of these rows. So R specifies like which of these rows you're in. So now initially you have like a stack, like you have a 3D. And then after you kind of like look into D and compute this term, D, now you're given like the actual like direction stack. And now within that stack, you have a bunch of rows. So like kind of like what size C, the number of columns, like that's the row size. So like, and now like to isolate to kind of remove all these cells and like get this exact thing right here, right? That's what R takes us. Like this is D. And like from R, we basically kind of like let's say like this is like the second like 0, 1, 2, the third row. So like R is like 2, 0, 1, 2. Then by multiplying R times C, like 2C, we basically like that's 1C and that's 2C. And 0 index, we end up right here. So like R kind of like puts us on like the actual row. And then C, which is like our column index, just kind of like gives us the exact cell. So then from C, like we hit the exact square that we want, the exact cell. And this is like kind of like the grand formula where we take this whole image stack and like we can kind of like, this is kind of a logical connection between like the flattened vector. And of course we append everything to this whole gigantic list of size, like a very giant list, and we add pass. So like the length of everything is like number of rows times number of columns times number of directions. And that's like the actual like size. So basically, yes, number of rows, number of columns, have a number of directions, plus 1. And that is a very large value, like 15 rows, 20 columns, times, well, actually like 6 cardinal directions, like we're assuming instead of 8 cardinal, just like 6 cardinal, like our coin we can launch here, 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 and here, like this way, that way, like all these kind of like pretend they're arrows, right? And then I'm gonna do times 2 because like if we can launch this way, we can kind of launch here. We can like launch like full strength, half strength, full strength, half strength. I'll determine the exact intensities later. I was actually doing some like tests based on BumperCoins, and I actually like came up with some numbers. I believe like the big one would be like 0.4 if a max, and like this one could be like 0.2 or something. And then like plus 1, where 1 is for the pass. So this is a pretty big number, right? Like 15 times 20 times 6 times 2, 36. Oh, very neat. Very nice number, like full 360, like 36001. Very nice. 36001. So like our actual policy network here would be a vector of this length, which I mean, it's a pretty complicated, like at least to me, like if your image classifying a digit between 0 and 9, right, then the output is just a vector of like size 10, like softmax, right, cross entry, whatever. Let's just like the resulting vector, the policy distribution between like 0 and 9, so it's like size 10. Whereas here, 36,000, pretty big. So training it would take quite some time. I'm assuming, right? So it's a pretty complicated thing, right? All policy actions. Again, like if you were to ask, like if you were to kind of like ask, like in this vector, like you want to know the significance of like the ith, like the ith entry in this vector, and like this is like p of theta, like this is like your policy vector. I'm so used to p being projection, but yeah, here's like p theta of s of your state. Like it's like some some list, and like what you want is like if you want the ith entry in this list, well, how do you do it? Like what does that mean, right? Like because these are just a bunch of numbers. Like again, you have to basically like reverse engineer this formula. So like you use kind of like mods. Well, if it's the last entry, we know it's like the probability of the past action. We're assuming that this vector is being normalized, right? So if you have like say like the what's 15 times 20? I think it's like 300, right? So like if we have like entry 305, right? Then like what is like, so like given like our DRC, we can kind of compute like the index here. But now given the index here, like when our neural network spits out this like list of this size, like how do we actually work out like what that means in terms of the policy, right? Let's just say that like we have, well, like 305, what that means is like we kind of reverse engineer this formula. So like we take this number of rows times number of columns, which is like 300, because we have like 15 rows and 20 columns, right? So like this size is basically parentheses like equals 15 times 20 equals 300 in BumperCoins, in my abstraction, in my discretization of the state space. Again, it's a continuous thing. I'm just kind of like bucketing it to just simplify to let this algorithm run, right? So, to like say like, hey, like if we're given like the 3/5 like in zero index, like the index I is 305, right? Then like what does like this kind of actually mean, like in terms of like the policy, right? So we take this number 305, and we actually like we start off by modding it on 300, right? We mod it by 300. And what this does is it will give us 5, right? That means like if we actually like kind of like look inside like this flattened wait, where's the flattened distribution? Like right here, right? Like this is our actual thing. Its length is 3601, or is it an extra 0? Wait, what? It has to be 001, right? 36. Yeah, 001. Right? So now like what is the actual length of this, right? Its length is 300, correct? Because like that's like 15 times 20, like one whole plane gets mapped onto this. So the indices that this covers based on 0 indexing is 0 to 299, right? And then the index that like this segment covers would be 300 to what? 600 minus 1. To start the next one, minus 1. That's like 599, right? 599. In the index we care about, 305, right? So by modding that by like 300, what we've kind of isolated is like 5 here. So like 0, 1, 2, 3, 4, 5. Right? So like first what we do is like we take this, like 305 actually, and then we would divide the integer division, that means we truncate down, by 300, and that equals 1. So we know that we're in D, the direction we know by doing this division equals 1. And now we mod by 300 because we're done with D. Now it's just like we've kind of figured out what D is, and we just want to get R and C, right? So now we have 5, right? And then actually, for just to make it interesting, let's, instead of 305, let's make it 325. Intentionally, because I want to make this thing larger than 20, the column size. Again, 325 divided by 300 is still 1. That changes nothing. But now 325 mod 300 is 25. So now it's like, again, like we've kind of, we want to figure out instead of 305, we want to like do 325, right? So by modding by 300, we've kind of like we're kind of like no longer kind of in like this image stack, like 3D dimension, like in the stack of image stacks. Like now by modding by 300, we've kind of like specified exactly, like now we're like by modding 300 and getting 25, this 25 is kind of in the perspective of a given image stack, right? In particular, like we know D is 1, so like we kind of want to like take 25 in zero indexing. We want to take the 26th element in this list because of zero indexing, right? So it's like we count like 0, 1, 2, 3, 4, dot, 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 19, 20, 21, 22, 23, 24, 25. That's kind of like visually where it is in the plane, as if like, even though it's flattened, like in the actual plane, right? It'd be like, anyways, the point is we can kind of like recursively do like the same kind of, it's like if you're more familiar, like mixed radix numbers, right? Like mixed radix numbers. Kind of like time. Anyways, I digress. So now we have 25, right? So like that's how D equals 1. And then 25, what we do is we take this and we both divide by 20, and we also like do the same thing. Like just like we did by 300, we do this by 20, right? Where 300 kind of comes from here, and that's the size, right? That's like the size of each row as the number of columns. So 25 divided by, so like now we know D equals 1. So now 25 divided by 20 equals, again, truncates down to 1. So we know D equals 1, and now we know R equals 1. R equals 1, right? So then 25 mod 20 equals 5. And now C equals 5. And we're done. This number, 325, in our policy, like the 325th, that means 326th, because of zero indexing, entry in this gigantic policy vector is the distribution of the coin specified by, it's the coin specified by coordinates 1, 5, like in our 15 by 20 like grid, right? There is like we take the first row, like that means like we jump past 0 all the way to 19, right? And then 20, 21, 22, 23, 24. Yes, I know I can't read this. 25. That is 0, like 20 is like 0, 21, 22, 23, 24, 25, like 0, 1, 2, 3, 4, 5. So like in this row, so like the row is basically like 1, because like we skip past the 0 and we go to 1. 0 cars are 19. We're in row 1, that's R, and C equals 5. So in 0, 1, 2, 3, 4, 5, the 6th one, because zero index, and that's it. For this game, like if you actually go to like 20, like the 25th, like the first row, so first row and 5th by zero index, like 0, 1, 2, 3, 4, 5. So this cell right here, if this were a coin right here, if there were a coin here, again, the policy vector we output doesn't actually have to be legal. Like we have to like kind of like look at the coins, and then like we have to filter out all the illegal policies, because what it's saying, like let's just say that like this, let's say that like P of like this policy vector of 325 equals 0.05. So it's saying that like there's like a 5% probability, like 0, 1, 2, 3, 4, 5. I mean, it's saying that like it takes this coin right here in this cell, and then it wants to like it has some decisions to make, and there's a 5% chance it'll move this coin. And where, you might ask, does it move this? Well, it moves this in the direction of 1, which if you look back to our initial thing, says like, hey, like take this coin here, 0, 1, 2, 3, 4, 5, and with 5% probability, move it like in this general direction, right? Like I think 60 degrees, because 360 divided by 6 is 60, and move it there. So that's like, that's kind of like how like we have a huge policy vector, very huge policy vector, like this policy vector, probability vector, or all possible actions is very huge in BumperCoins. So basically what I'm trying to like get out of all of this is like designing the actual network. I mean, it's a very large network. So like when we actually run, like when we actually do policy iteration, like we actually like have it self-play, like the bot plays against like the bots we instantiate two bots with the same AlphaZero like network. They play against each other, and then like it gives a set of like whole training examples, right? Like we have a whole bunch of training. Like what I'm saying is that like it'll be a huge pain. It'll require like lots of like computation. Like it's a lot of work to like train the neural network. And like just for like I think that like it's better for me to start like with just like a simple game like Connect 4 where like the actual like neural network architecture like the neural network architecture will not be so very kind of the sizes will be much more scalable. Like I mean much like it's more of like a toy example. And my idea is to first like implement AlphaZero just for Connect 4 and then I'll try to like abstract the code and like make everything kind of like super abstract, like deal with like use object oriented programming, like have like a Monte Carlo tree search class, like a Monte Carlo class with all like the tree search implemented. And I kind of want to make that very abstract so that I can just plug it into my game, like from Connect 4, just copy and paste it onto my game and just have it work. So if I kind of get it to work for a small toy example, I just have to swap out the neural networks and like some of the game logic and just plug that into like my Monte Carlo file and just like have it train everything and like get it to work. So my idea is to like kind of starts with a small toy example and then like because like what I just did like all this kind of like all these kind of image planes and like kind of just working with indices like the row index, column index, direction index specifying which plane you're in, like all of that's pretty complicated. You're going to have a very large network. And we're actually implementing like the AlphaZero algorithm, like doing Monte Carlo tree search. And like, I mean, like when you're actually implementing AlphaZero, like in the self play and like getting like a list of like sample points to like train. Cause like you have like every time you like AlphaZero, like you have like two bots at the same network. They play each other. One of them wins or it's a draw, whatever. There's some outcome. And now you have all the state action outcome pairs, like state, like, and then like from that, like, and the also like, and you have a policy, like the Monte Carlo tree search kind of gives you a policy. So like by playing one instance of the game against each other, like you get a whole bunch of training data, and to actually like train that to like update the network, and you get a whole like kind of it's like a feedback loop of like the network. You play with itself, you get some like training data, you use that training data, and then you kind of improve the network. So each time it iteratively improves. Like again, like it's like iterative, like that's the AlphaZero like thing. It's like policy iteration through self play. So like this network training the network for BumperCoins is like going to be a very kind of complicated network. It'll be like a very time consuming process. That's why I think I'll start small and like make sure that my Monte Carlo, my AlphaZero code works for the Connect 4 toy example, and then from there I can like swap the BumperCoins code to make it work for my game, and that's like the approach I've decided to take. So this whole like live stream so far was my kind of introduction between my ideas. Like I've definitely done some contemplation beforehand of how my neural network for BumperCoin should be, but like the point is that this is a huge hassle and like it would suck to write everything and have something go wrong. So I'll first start off small with just a small Connect 4 example, and then I'll basically swap out a neural network. I'll like have a new neural network model and then train that instead, like afterwards. So I'll first get it to work for Connect 4 and then I will graduate. Like once that like works, I will implement it for my own game. So that's my idea, and I think I'm pretty tired now, so I'll just kind of stop and yeah, that's all for now. Like the next time I'm going to actually like work on Connect 4 exclusively. So I'm taking a bit of a detour and like I'm just like this whole like process was for me to just give my motivations on why I'm taking a detour. And from now on I'll be working on Connect 4 stuff. All right, that's all.